Okay, let's take a look now at carbohydrates, lipids, and proteins. And we are going to be examining their structure and nomenclature. So the first thing we need to look at is a bit of structure. So we'll start with a small carbohydrate. In this case, we're going to be looking at a 3-carbon molecule. Carbohydrates have characteristic hydroxyl groups on the carbons, which adds to their polarity and great solubility in an aqueous environment. And this particular 3-carbon carbohydrate is going to have an aldehyde group. This aldehyde group is on the number 1 carbon. We name these number 1, 2, and 3, starting with the aldehyde group. And the first thing to notice is that this 3-carbon backbone is similar to the glycerol structure. So if we replace this aldehyde with another hydroxyl group on the number 1 carbon, this would be glycerol. Because we have the aldehyde on here, the name of this is glyceraldehyde. Now glyceraldehyde is structurally related into the carbohydrate family, and because it has 3 carbons on its backbone, it is considered a triose. Recall that the suffix OSE refers to carbohydrates, and tri refers to the 3-carbon backbone of this particular carbohydrate structure, glyceraldehyde. Now, if we make a small rearrangement in the glyceraldehyde molecule, we would see that this 3-carbon backbone can be adjusted to form a ketone in the center of the molecule. Now we're just doing a functional rearrangement here, so we can rearrange these groups, the hydroxyl groups there. And now we have a ketone on the number 2 carbon. We still have a 3-carbon backbone, which is the glycerol backbone, but with the ketone group inside, we have essentially created an acetone-like structure. So 3 carbons with a ketone in the center is acetone. Now the fact that we have 2 hydroxyls on the number 1 and 3 carbon makes this dihydroxyacetone. And so hence that is the name of this structure. Dihydroxyacetone. This structure is also a triose because it has a 3-carbon backbone. Now if we take the nomenclature of these 2 trioses just a little bit further, we would see that this structure here is also called an aldose. Aldose is the general name for carbohydrates that have an aldehyde group. Likewise, with the dihydroxyacetone, this is called a ketose. And a ketose are carbohydrates with a ketone functional group. Now, if we expand our nomenclature into more complex carbohydrates, let's say, for example, the 6-carbon backbone that we will be studying quite often. This 6-carbon backbone is a hexose. Hexose meaning 6 carbons. So the first structure we're going to look at is an aldose structure. We have an aldehyde group on the number 1 carbon. Now in this structure we have hydroxyl groups coming off each of the carbons. And fill in our remaining bonds with hydrogens. And notice what we have here with a hydroxyl group, an alcohol group on the right of carbon number 2, flip to the left on carbon number 3, and then on the right-hand side, remaining down. This is the structure of glucose. Glucose is the major energy source of our body, and we'll be studying this quite a bit for the rest of the semester. So glucose is a hexose, its general name. And of course it's also an aldose because it contains an aldehyde residue. Now if we modify this structure of glucose into a ketose, we are keeping the hexose backbone because we have 6 carbons, of course, but now we are going to modify the aldose into a ketose. So we will do a similar rearrangement to put the ketone group on the number 2 carbon. And then we fill in our OH groups for the rest of the molecule. And of course complete the bonds with our hydrogens. So these two molecules are obviously related. They're hexoses. One's an aldose, one's a ketose. And when we change the aldose structure of glucose into a ketose, we now have the carbohydrate specifically called fructose. And recall that fructose is a large part of our diets. Now the next thing we have to look at is the structure of glucose in its actual form. This structure of glucose here is of course the Fischer projection. And the reason we draw the Fischer projection for glucose is out of convenience. Now this of course is not what glucose looks like in the body. Glucose looks like a ring structure. So how do we convert the Fischer structure into the cyclic structure that is the most common form of glucose? Well, the first thing we're going to do is we're going to take our Fischer projection as such of glucose, and we are going to take this Fischer projection and we are going to turn this and lay it down on its side, and we are going to turn this 90 degrees in a clockwise direction. Once we do this, we will now have this molecule on its side, and then we are going to take the oxygen of the number 5 carbon, and this oxygen is going to form a nucleophilic attack on the carbonyl of the aldehyde group on the number 1 carbon. The intermediate structure of that will look like this. Here's our number 5 carbon, hydroxyl group coming off of this residue. Here is our aldehyde group on the number 1 carbon, and these electrons here will attack that carbon. Now what this will give us are essentially two configurations. The two configurations arise because of the free rotation around the bond between the number 1 and number 2 carbon. So if we have our carbonyl with our oxygen facing down when the oxygen binds to this carbon, we will have this structure of glucose. Notice the number 1 carbon. If we have this attack of the oxygen on the carbon with the carbonyl facing down, the hydroxyl group that forms from this reaction is going to be facing downward from the ring structure. This is considered alpha glucose formation. So the alpha form of glucose is with the hydroxyl and the number 1 carbon facing down. Now, perhaps this bond will rotate and the carbonyl will face upward when the oxygen attacks. What will our structure look like then? In this case, the hydroxyl group will face upward. This is configuration of beta glucose. So if the hydroxyl group attacks the carbonyl of the aldehyde with this bond rotated with the oxygen facing up, the resulting product will have the hydroxyl group facing up, giving our beta glucose structure. Now, the reason we're paying so much attention to the alpha and beta glucose structures is because we need to talk about our major dietary carbohydrate. The major dietary carbohydrate that we ingest, which is our major energy source, is starch. So starch is essentially a polymer of individual glucose monomers, and these are linked covalently using alpha-1,4 O glycosidic linkage. Now, what is an alpha-1,4 O glycosidic linkage? So let's draw our glucose molecules together. Here's our oxygen, our number 6 carbon, faces upward. And what we need to consider is the alpha linkage between the 1 and 4 carbons. So that means that we are going to have number 1 carbon here, number 2, number 3, number 4, number 5, and number 6. If this is an alpha linkage, that means that our number 1 carbon needs to be in the alpha configuration. So the hydroxyl group will be facing downward. Now we're talking about a polymer of glucose, so let's put another glucose molecule here. Again, this is the alpha configuration. Again, our number 1 carbon of the next unit of glucose in this polymer is an alpha configuration. Now, how do we link these two together? This is essentially a dehydration reaction. So we are going to be removing water in forming this linkage between the number 1 and number 4 carbons. Hence our alpha-1,4 linkage. So this linkage will look like this. If we draw our two ring structures as such, this linkage will have oxygen linking both of the glucose monomers into an O-glycosidic linkage. In order to do that, we are going to be removing water from the reaction, hence being a dehydration reaction. Now this is the linkage of two monomeric units of glucose, so this is considered a disaccharide, but starch is a very, very long polymer. So what we can do is essentially form another linkage between the adjacent glucose monomer between these alpha 1,4 linkage here. And so we will form another alpha 1,4 linkage. Now, starch is a very, very rich, dense molecule of glucose monomers, and so starch also has the opportunity to branch the structure of the polymer. When we branch the structure, what we will be able to do is form another polymer of glucose adjacent to the first polymer and link them together. And the branches will be alpha 1,6 O-glycosidic linkages. So in order to consider this structure, we have to continue our number 5, number 6 carbon, our numbering system. And what we're going to do is we are going to link a glucose polymer from the number 1 carbon of a glucose molecule that has been linked to another polymer. Here's our 1 and our 4. This is our alpha 1,4 and our linear polymer. And here what we are going to do is, again, we are going to have another dehydration reaction. We are going to be removing water here, but here we are now going to link this oxygen with this carbon bond, hence it being an alpha. The hydroxyl group is facing down, 1,6 O-glycosidic linkage. Now starch again is very long polymers. There are many, many, many glucose linked together. And we also have these branches giving an increase in the density of glucose in a molecule of starch. Now the frequency of these branches, of course, will indicate the density of the starch molecule. And these happen every 24 to 30 monomer units of glucose. So that means as the polymers linked up, if you count 24 to 30 of these, you will have an alpha 1,6 linkage to form the branch structure. So starch is our most dense and most common source of glucose, which we'll be studying in energy production. But there are a couple other molecules of carbohydrate in our diet we need to consider. And this, of course, first one we can talk about is sucrose. Sucrose is a disaccharide. A disaccharide is 2 monomeric units of carbohydrate. And so sucrose is a disaccharide of glucose linked to fructose. Now, you might ask, why do we have this as our sugar source when we could just use glucose, which is our major energy source? The question here is answered by considering sweetness. The taste of sucrose is much sweeter on the tongue than glucose. Glucose actually does not have much of a sweetness to it compared to sucrose. So the sucrose is more common in our diet for this reason. Now another carbohydrate that we use is lactose. This is also a disaccharide. Two monomers work linked together. The first one is galactose, and this is linked to glucose. And lactose is found, of course, mostly in dairy products, such as milk. And in dairy products, the lactose provides us with a large component of carbohydrate in the form of the galactose-glucose disaccharide molecule. Okay, let's now transition our discussion into lipids. So dietary lipids come in two forms. The predominant form of dietary lipid is a triazyl glycerol. Now, triazyl glycerol is the most common form of fat in our diet, and again, it is going to have a glycerol backbone, hence glycerol. Now, in this glycerol, we are going to have our true hydroxyl groups on the number 1, number 2, and number 2 carbon, 3 carbons. But in order to form the dietary lipid, we are going to be substituting onto these alcohol groups with fatty acid moieties. So a fatty acid is the common form of our fat that we ingest. And we'll look at these structures a little bit later. But suffice it to say that fatty acid means it has an acid functional group, which is a carboxylic acid, and a fat that's going to be very hydrophobic, so it's going to have a long hydrocarbon chain. In order to form a triglyceride, we are going to essentially dehydrate this, bond here, we're going to be removing water, and we are going to be forming an acyl linkage between the fatty acid and the hydroxyl group on the glycerol backbone. In fact, we are going to do this 3 times. So we are able to link 3 of these fatty acids to the glycerol backbone, hence giving it tri-acyl structure. So what the triglyceride looks like in its final form, we have our oxygen here, we have our carbonyl, and we have our long-chain fatty acid. Now notice how I've drawn this structure. This is an acyl linkage, and I have CH2, CH2N, because this number of these CH2 groups are variable, but the fatty acid will always end with a methyl group, CH3. We will have 3 of these on these carbon backbones of glycerol. I will just refer to this as R, being the long hydrocarbon chains. If we complete our hydrogens on our carbon backbone, we have the complete structure of a tri-acyl glycerol. And this is the major form of our fats in our diet. Now let's turn our attention to fatty acid structure. What is a fatty acid? Again, a fatty acid is a long chain molecule. Being an acid, it's going to have an acidic group on the end, and it is going to have a long hydrocarbon chain. This is an exceptionally energy-rich molecule. We will see when we begin to oxidize this molecule how much energy that we can extract from it. Now I'm just drawing here a number of carbohydrate residues, number of hydrocarbon residues, structures, in order to just get our nomenclature correct. So the first carbon, the number 1 carbon, is considered the carboxylic acid carbon. Number 2 is the next CH2 carbon. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this particular fatty acid has 12 carbons to it. In order to properly designate this, we are going to call this first 12. Now, the other feature of fatty acids is that we can have unsaturated bonds. What that means is that somewhere in this chain we can have double bond character. In this particular structure here, we don't have any double bonds, so this means that this is a completely saturated fatty acid, which means that all of these carbons are saturated with hydrogens. So we would indicate this by indicating 12 carbons long, colon, 0. This is the formal name for this particular fatty acid. 12 carbons long, no double bonds, completely saturated. Now, what if we were to add a double bond in here? So we're maintaining, for example, our 12 carbon structure. So that doesn't change. But now we've introduced a double bond. Introducing one double bond makes this a mono unsaturated fatty acid. In order to correctly label and describe this fatty acid, we are going to indicate that there is one double bond, and this double bond begins at carbon 1, 2, 3, 4. And we put delta 4. So with 12 carbons, we have one double bond, monounsaturated. We indicate which carbon that the double bond starts at. So it's 12, colon 1, delta 4. Now, what if we introduced another double bond? Then it would be considered a polyunsaturated fatty acid. We would simply name that fatty acid by its 12 carbon length. We would indicate 2 double bonds, and then we indicate which carbon that those double bonds begin at. The first one we know begins at number 4, and let's say the next one begins at number 8. So from this information, you should be able to take the structure of the fatty acid and correctly name it by this nomenclature, and also perform the reverse. Take this nomenclature and be able to draw out what the fatty acid looks like. Another point to consider is that these double bonds can either be cis or trans. However, in our bodies, cis is the only form of double bond that we can make. Now you can imagine if there was a double bond here in a cis configuration, this fatty acid will actually be kinked. So where do trans come from? Trans double bonds come from industrial processing. The purpose of trans is to increase the shelf life of food, because trans double bond fatty acids are more stable and less prone to oxidative damage. So hence, industrial processing includes trans to increase the shelf life. Now, what about proteins? Protein digestion, we need to consider two aspects. When we consume our dietary proteins, the proteins are in their native configuration and their final form because we have obtained these proteins in that form. So the first step in protein digestion is to take the protein and denature. The purpose of denaturing the protein, which is also equivalent to the word unfolding, is to expose the peptide backbone to enzymes that are going to hydrolyze the protein into amino acids. So these are going to be a series of hydrolysis reactions to release the protein into its respective amino acids. Now, how do we denature? Well, this is where we talk about gastric pH. We know that our stomach pH can actually decrease down to approximately 2. What the acid environment is going to do is this acid is going to facilitate the denaturation of the protein. Remember, acids, we have a high proton concentration, and this is going to interrupt and interfere with bonds that hold the protein's tertiary structure together. So with increasing amounts of proton, meaning lower pH, we are going to take the protein from a tertiary to secondary structure. And then recall, secondary structure is largely held together by hydrogen bonding, and so this will be denatured into primary structure. So the low pH is going to come from the stomach. The stomach has specialized cells that are called parietal cells. And these cells are able to simply perform a reaction that takes water and adds to the water carbon dioxide. And what we are going to form by this chemical reaction is bicarbonate ion plus a proton. This reaction is enzyme mediated, and the name of the enzyme that performs this is called carbonic anhydrase. So carbonic anhydrase, which is located in the parietal cells in the stomach, which is in the lining of the stomach, takes water, which there's plentiful amounts. It takes CO2, which we will see this comes from respiration. And this is during the energy production process. We'll see a lot of this later. And combines these two molecules to form a bicarbonate ion, and most important, a proton. This proton, of course, is what is contributing to the decreasing pH in the lumen of the stomach. This gets transported into the lumen of the stomach, and there it combines with chloride ion to form hydrochloric acid. So this process is by lowering the pH, which is going to unfold and denature the protein. Now once we have the protein unfolded and denatured, then we can perform our hydrolysis of our peptide backbone. In the primary structure, all of the peptide bonds are fully exposed. So what we are going to want to do next is to digest the protein into amino acids. I'll just draw a little bit of a protein here. Here's our R groups. Here's our primary structure that we have now obtained from the low pH denaturation reaction. And so now what we are going to do is we are going to attack with water these bonds. So for example, let's say that this is a very short protein. Let's say this is the N-terminus. Let's call that the C-terminus, C-terminal end. What we want to do is we want to add water across this bond. The water will attack the carbonyl to disrupt the peptide bond. Now, of course, this is mediated by an enzyme. The enzyme in the stomach is called pepsin. So pepsin will take this structure and add water across the peptide bond, and in doing so, release the amino acid. Now, pepsin is able to do this with many of the peptide bonds, and so that is going to slowly degrade the protein. Now, what prevents pepsin from doing any damage outside of the stomach? Well, that's because pepsin is synthesized by cells of the stomach These cells are called chief cells, and it's synthesized as pepsinogen. Pepsinogen is considered generally class of zymogens. These are inactive proteases. Now, a protease is any type of enzyme that is able to digest and break down a protein. Remember, ASE, that suffix stands for enzyme, and the first part of the word, it stands for protein. So it's a protein-degrading enzyme. So the cells of the stomach make this in an inactive form. This is secreted into the stomach, and once it's in the stomach, with the low pH due to the high concentration of proteins in the lumen of the stomach, this will convert the pepsinogen into pepsin, which is now an active protease. The pH optimum for pepsin is approximately 2 to 3. This is a very important feature of this particular enzyme. So if we look at pepsin activity as a hydrolytic enzyme to digest protein, and we look at pH on the x-axis, what we would see with this enzyme is activity like this. So the peak activity of this particular enzyme is going to be around 2 to 3. The reason this is so important is because this is the pH of the intestine, neutral pH. So once the digestion occurs in the stomach because of the acid-mediated denaturation of your protein, pepsin-mediated hydrolysis of the peptide backbone to release amino acids, then all of that material is shifted into the intestine. We do not want this pepsin active. We have other enzymes we'll see in a later video to continue digesting proteins, but we want this pepsin to become inactivated. So once the enzyme exits the stomach and exits its optimal pH environment, it gets into the neutral pH of the intestine, and the pepsin is no longer active. So it is a self-limiting enzyme.